So we've seen that you can use delta H, or a change in enthalpy, to calculate how much heat will be released. And we did this in a last video using the delta HF reaction, and we saw that the heat was either equal to the mass times the delta HF reaction if you have it in joules per gram, or oftentimes if we're doing reactions, we'll do it in moles. And just like in gas laws, N is a number of moles. So the heat is equal to N times a delta H. And sometimes we have to add a delta H of reaction factor in there to take care of the stoichiometry. We can also use something called heat capacity to calculate the energy change. Because if you really think about it, the energy needed to change temperature depends on a couple of things. It depends on what are we trying to heat up. We've all seen that if you're going to heat up a pan on the stove, the pan itself heats up quite quickly, where if we fill the pan with water to start boiling for pasta, we'll spend a lot longer time waiting because the water in there also needs to absorb energy. So the energy needed depends on what it is we're trying to heat up. It also depends on how much of whatever substance we're trying to heat up. A big pot of water for pasta for a family will take a lot longer heat to heat up than a smaller pot of water if you're just going to make ramen noodles for yourself. And it also depends on how much we need the temperature to change. If we just want to warm up the water a little bit, it won't take nearly as much time as if we're going to heat it up all the way to boiling. And so these are really our two big equations. Q equals M delta H, or N delta H if I'm working in mass or moles, if I have the enthalpy given to me, or I have this guy, what I like to call Q equals MCAT, because MC, and then this kind of looks like an A, the delta sign. You remember from our very first video on thermochemistry that delta means change. So in this case, I have a change in temperature, which is not something that I saw in my earlier equation when I was just dealing with how much heat came from 4.1 moles of sodium hydrogen carbonate. So remember, change in temperature is defined as the final temperature minus the initial temperature. T final minus T initial, just like we did in our endo-exo lab. So let's talk about this CP. That's the specific heat capacity. We can talk about heat capacity in two ways. We can talk about the heat capacity, and we can talk about the specific heat capacity. Okay, heat capacity is talking about a particular object. When I do this in class, I like to walk around and say that I need to find out about Joe's frying pan versus Tate's frying pan, and how I would have to break into their kitchen and get both of their frying pans and go compare how much energy did it take to heat up Joe's frying pan versus Tate's frying pan. That's a heat capacity. The specific heat capacity goes to talking about a particular substance. I don't have to get Joe's pan and Tate's pan if I know they're both made out of stainless steel. I can get the mass of the pan and use the specific heat capacity of stainless steel to determine the amount of energy. So if you look at the units are different. Specific heat capacity is in joules per gram per degree. That's because that's any object made out of that material. So I need to find out what the mass of the object is. The heat capacity for an object is just in joules per degree. So it's really important to look at your units and let that drive what you need. Because in AP, I've seen a lot of people insist they need to find a mass somewhere to put in when they're given a heat capacity. And if you look at the unit, there's nowhere for there to be a mass. The only time you need a mass is if you're dealing with the specific heat capacity. And so thinking about heat capacity leads me to this question: which has a higher specific heat capacity, iron or water? Well, think about how long it takes to heat up metal versus water. If I put an empty pan on the burner and turn it up to high, before very long, I'm going to burn myself if I touch it, because it does not take a lot of energy to heat up a metal pan. If I turn the burner up to high and wait for 2 or 3 minutes with a pot of water, after 2 or 3 minutes, I can probably stick my finger in there and find that maybe it's a little warmer, but it certainly wouldn't burn me. So it takes a lot of energy to cause a small change in temperature in water. So if we think about that, big temperature change for small joules means that this has to be a small number. Small temperature change for joules means this is going to be a bigger number. So since iron heats up faster, it must have a lower specific heat capacity. And if I take a look at this, I'll find that this is on here in joules per gram C. Iron is 4.50. Water is 4.18. So you can see that the heat capacity of water is 4 times larger than the heat capacity of iron. So water takes 4 times as much energy to heat up even 1 degree. So let's use this Q equals mCdT equation. And we'll look at how we can rearrange this to find information. So how much heat is required to raise the temperature of some water that has a mass of 249.6 grams at 23 degrees to 27 degrees. So there's 2 things I see here that are giving me a hint. One, I see a change in temperature. Okay? So change in temperature, if you think back to that first slide, I had 2 equations. One had a change in enthalpy, and I don't see that in here anywhere. The other, Q equals mCdT, had a change in temperature. And I do see where I can calculate a change in temperature here. So change in temperature tells me this is a Q equals mCdT problem. So like all math problems, I write it, I solve it, I math it. So I write it down. I find what my delta T is, so final minus initial, 27 minus 23, 4 degrees. And I know the heat capacity of water from the last slide is 4.18 joules per gram per degree. So if I solve this equation for Q, heat, everything's all set up. I just have to sub this in. So the mass is 249.6. Okay. The heat capacity, we looked that up on the last slide, 4.18. And the change in temperature, which I calculated, 4.0. And all I have to do is multiply these together and I'll get a number in joules. So I get 4,173. So actually, really, I have 2 significant digits here because that's 4.0 C. So 4,200 joules or 4.2 kilojoules would be an acceptable way of putting that. So let's take a look at doing this and rearranging for a different variable. So now I want to solve this equation not for the heat, but for the specific heat. I still see there's a change in temperature here, and also I have a really big hint that I'm looking for specific heat, and only one of our equations has specific heat in it at all. So we would have to use Q equals mCat because it's the only equation that we have that uses specific heat. I'm going to need the change in temperature. So my final temperature was 39. My initial was 19. So 39 minus 19 is 20 degrees. And in this case, I don't know what the specific heat is. I do know the mass though. The mass is 258 grams. So I take my equation and I'm going to solve this equation now for the specific heat. That means I'm going to have to divide both sides by mass to cancel out the mass, divide both sides by change in T to cancel that change in T. So I write it, I solve it, and now I can put my numbers in it. Q is 4.9 kilojoules, and usually specific heat is done in joules per gram per degree. So I'm going to go ahead and change that to 4,900 joules divided by the mass times the change in temperature. Mass is 258, change in temperature is 20 degrees. And when I do that, I want to make sure and check. The unit I was seeing before is joules per gram per degree. So there's a joule on the top, per gram, per degree. That looks like a unit for specific heat. And if I do that math, I get 0.95 joules per gram per degree. And let's try one more just to see what else we can try getting out of this. So in this case, I have aluminum, and I've been given the specific heat of aluminum. It's heated with 76 joules of heat, and it starts at 64.1 degrees C, and it wants the final temperature. So again, I notice I've got specific heat here, and I'm looking for a temperature change, so that tells me I'm doing Q equals mCat. And I remember that the delta T is T final minus T initial. So I'm going to go ahead and put that into my equation and solve it. So mCp delta T is Tf minus Ti. So I want to get the mCp out of the way, so I'll divide the Q by mass times the specific heat. And that would give me Tf minus Ti by itself, so I need to add Ti to both sides. And I get my change in temperature. So I've written it, I've solved it, I math it. 76 joules, that was the heat, so that goes where Q goes. 9.03 grams, 0.982 joules per gram per degree. So again, if we take a look at this and we use our units as a guide, there's a joule on the top and a joule on the bottom. There's a gram here and a gram here. So the unit left is degrees C, which makes sense because I'm adding that to a degrees C. So I'm going to do this math first. Take 76 and divide it by 9.03 times 0.982. And then that will get me 8.57 degrees plus my initial temperature. That makes sense. I'm heating it, so I should expect the temperature will go up. And I get a final temperature of 72.7 degrees. So you can see this is a very versatile equation. I can move a lot of things around and get lots of different answers.